everybody. Today our webinar is on innovative optimization technologies for performance, cost, and lightweighting. To give an introduction about DEP, DEP stands for Data Engineering Products, and we were founded in 1998, and we are the creator of the MeshWorks platform. And we have our in-house and global R&D centers in different geographies. Our headquarters, it's in Troy, Michigan, and we have our own offices in India, Japan, China, and Brazil. We do have our distributors in different locations. When it comes into our offerings, we have 4 different offerings. One is our engineering consulting, which takes care of all the consulting projects. Software development and solutions group, they actually work on creating and developing the MeshWorks software. Next is our product development group. This works on new product solutions all the way from the concept to the manufacturable part. And we do have a talent acquisition team which takes care of all the on-site requirements for contract placements across various geographies. Coming into the DEP team, DEP has 500 plus engineers, and 20% of which is PhD, 70% masters, and 10% bachelors. Our headquarters is in Troy, Michigan. Okay, and we also have a presence in all the geographies that were highlighted on the screen. Like we have our office in China, Brazil, India, Japan, and our distributors in Europe, Korea, and Japan. Now coming into MeshWorks 2021, it's a CA parameterization tool which helps to convert the FE or CFD models into intelligent parametric CA models. Next is our morphing technology. With the help of morphing technology, we can get upfront design solution by performing morphing operations on the CAD and CA models. The next one is our design optimization capability. We have a multidisciplinary optimization enabling tools within MeshWorks, which is actually powered by all the parameterization morphing techniques, which in reality we only have to build in one model, and we can easily be transformed to other solver environments. Next is our process automation group. This group does all the automation tasks within MeshWorks for the customer requirements. As we speak, we have all our customers, they are trying to use MeshWorks process automation tools, which is actually benefiting them with 60 to 70% of their time saving in their day-to-day repetitive tasks. Next, a pre and post-processing tool. MeshWorks has a powerful pre and post-processor, which has a lot of automated modules for machine assembly and result exploration. And recently we released a tool called CONCEPTWORKS, which is a powerful tool to quickly create new architectural design changes or quick conceptual studies. Coming into our application in different stages of the product development cycle, the graph clearly shows like the new trend with MeshWorks and the current trend. With MeshWorks, you can have a heavy loading happening in the conceptual stage, wherein we'll be working with the legacy models and doing all the model changes with an existing legacy design. And you will have pretty much 90% frozen design at the end of the conceptual phase itself. Finally, you will have a little amount of changes which would be required in the detail phase, followed by visual validation and maintenance. Different modules play different roles. MeshWorks morphing and concept modules play in the first phase. Then in the middle, parameterization, CA and topology tools comes in the picture, and later our quick meshing and assembly modules will play the role. Coming into the challenges of lightweighting and mass savings, we do face a lot of challenges. To achieve lightweighting, we may have to go across multiple tools, and it's pretty time-consuming task. And when we, as a CA engineers, like to drive the design, then there is a challenge there too. And in case if we need to make design modifications or design space changes, we have a lot of challenges with the current tools that are existing in the market. And we are definitely looking for smart enablers to remove mass. And the optimization tools in the market currently requires multiple levels of skill expertise so that they can do the complete loop of optimization. And this webinar will also be useful to generate CAE, FEA, and CFD modelers. Coming into our solution lightweighting, MeshWorks has a rapid concept generation tool all the way from your topology results to a manufacturable part with zero CAD. Next is our our offerings in terms of the number of parameters or the library of parameters which MeshWorks offers. That is also something which our team will be sharing today. And auto-parametrization techniques. There is a lot of automated tools which has been recently added in MeshWorks, which in fact doesn't need the user to know all the manual steps in morphing. He can go with the auto-parametrization tools, which will directly create the parameters on your model. Next is our built-in DOE and optimization capabilities. Those are pretty handy for anyone to use it without switching to any other tools. Finally, converting the final CA optimized designs into a kind of representative CAD using your CAD morphing approach. So these are some of the solutions which we would like to highlight in MeshWorks. By saying this, I will hand it over to Paresh and Aditya to take it forward with the demos. Yeah.
Hi Raj, thank you so much for the introduction. So let's jump right into the demos for today. So first we will start with how MeshWorks is used as a pre or a post processing tool when it comes to our topology optimization. So let me go ahead and show you the demos. So as you can see, we have a casting component over here. And you can also see we have multiple rib locations to where we can very quickly defeature using one of our feature removal function. So to do that, we will first go ahead and create a skin mesh or a 2D mesh over the solid mesh. So once we have done that, we can quickly just click and go ahead and defeature it. So once we have accepted, it will very nicely remove the features that we have selected. So the next step, once we have defeatured, will be to create a design space to run the topology optimization. For that, you see we have a very nice function to where the user can create a boundary using a 1D mesh. And once we've created the boundary, the function will automatically go ahead and generate a layer of skin, which is then later we can optimize the volume by just selecting the elements. So once we have optimized the volume, we can go ahead and create a solid mesh. So this solid mesh or the 3D mesh is also node-to-node compatible with the base component. So once your design space is ready, the next step is to subject the component to a topology optimization. So once we have run the topology optimization as the result you just saw, we will use such results to create manufacturable ribs as the demo that you're going to see right now. So again, we have a casting component to where we have created a contact zone, which will act as the zone where we will create the rib. And as the first step, we will first go ahead and select 3 nodes on the intersection that I've already created. So once you've selected the 3 nodes, which will define the plane, and then I will select the node where the plane is going to be created. And I will input the parameters for the size of the plane and click on execute. So you can see the plane has been generated. And once I click on return, you can see there are multiple reference points. So I will select 2 reference points from point A and point B, which will act as the profile for the rib that I'm going to create. So once I've selected the reference point, I can go ahead and select sketch the rib and change it to smooth. So when I sketch the rib, I will also be able to modify the profile of the rib. So now the topology optimization result will come into play. For example, just assume this is the topology optimization result. I will put it in wireframe, and then I will modify the curve in such a way that it will mimic the topology optimization result. So once I'm able to closely modify the profile of the rib, I will click on accept, and then I will now input the parameters. So it can be any parameter depending on what the user uh, wants to change. So I'm just going with an element size of 3, and also I'm creating a fillet region. And also we can choose to remesh the fillets region. So once I preview the profile, I'll quickly go ahead and generate the tetrib. You can see how nicely and quickly we are able to generate it. So I'll just do an auto color. So now I'll hide half of the casting component to show you that it's a tetra mesh that is generated, tetra rib that is generated. So there you go. So in just a matter of minutes, with the help of the topology result, we are able to use some of the functions that are available in MeshWorks to quickly engineer such ribs. So the next one, we will see how we will use ConceptWorks, a module of within MeshWorks, to automatically generate a concept member using the topology result. As you can see, we have a topology output in front of us, and then we can create a trajectory using the topology result, and using ConceptWorks create a member function. It will very nicely read the trajectory, and it will with the parameters that we have inputted, it will go ahead and generate the cross section, and then a very nice member like this. So once the member has been generated, we can also create just say a sidewall joint by using the existing cross section of the member. So once I've selected or traced the cross section, I will select the component where the joint is going to be created. I'll specify the vector, and I'll also mention the height at which I want the joint to be created. You can see with just a few clicks, we are very easily able to create a manufacturable concept member, and a joint. So the next demo, we will see how we can use we can use ConceptWorks to create a front-end structure, again by using a topology result. So you can see the topology result, and we have the front structure to where we can very much use the existing cross section of the component. And with the ConceptWorks, the reference method, we will go ahead and first create two trajectories. And once we've created the trajectory, I will select the cross section, and very quickly we'll be able to create the front end structure. And also, just say if you want to also create the front shotgun of the vehicle, by creating those trajectories again by using the topology result, we will very nicely be able to create such complex structures very easily. Okay, so the next one, how we can use ConceptWorks to create a solid casting part. Okay, so here we have a design space and a non-design space. So first, once we get the topology result, we will select the guide curve, which can also easily be created, and we will create the sections. So these sections, we can create multiple profiles like I section or circular section, and then generate a beam like this. So once we have generated the beam, we will now join the design, the non-design space and the design space by selecting the source and the target face elements. So once I've selected it, I will go ahead and split the edges to make sure the number of edges are the same. So once I'm done splitting these edges, I will now go ahead and select the curves in a sequence. So this will help in generating the connection. So once the source is done, the target will be selected in sequence. So now we can very quickly go ahead and click on the connect option, and you can see the non-design space and the design space has been fused. So the same way, just say if you want to create your own profile, okay, by creating a closed loop like this. So once I've created the closed loop, you can see a CAD line as such will be created. So this will act as our source and the target profile. And I'm following the same method like how I did for the previous part. So I'll select it in sequence and quickly go ahead and connect it. We can also create multiple quick slot creation, wherein I will select a region and then create a profile. And using this profile, I can go ahead and very quickly create the slot. So it's pretty much how the user gets to create the profile. So it can be the next one. We can also create a rib on your the casting part. So we will follow the same, the procedure where we use the skin mesh to create a plane, and by using that we will generate the reference nodes, and we will preview the rib profile, and then very quickly we are able to create a solid rib. So moving on to the next one, we will see how MeshWorks is used in modeling, parameterization and optimization technology. So just say you have an orphan mesh, it might be an Abacus format or an Astran format, or even a CAD that's been given to the user, and we use MeshWorks to generate the MeshWorks database. So it will look something like this. So once you have you've done all your model setup, we can very nicely go ahead and create multiple parameters, and you can see some of the examples in front of you, starting from any shape parameter or your weld parameter, beads, bulkheads. So all these can be created. And once they are created, we can pretty much carry a DOE. So this DOE will give us a fleet of models. So once we get the models, we can run simulation and then again begin optimizing. So all these are possible using our MeshWorks module. So these are some of the examples. As you can see, we have a multidisciplinary parametric CAE model where you can create all such parameters like shape, gauge, connectors, like spot wells or your solid wells or your adhesives, stamp features, creating loads or casting features like rib creation. So we will now look into some of the enablers that we can create using MeshWorks. So you can see we have bead parameters, slot parameters. We have doublers. So these are some of the methods in which we can create the doubler parameters. And we have part extension parameters, the ones that you're seeing. So you can see we even have a shell rib parameter where you can parameterize the number of shell ribs, and this is a welding parameter. And you can see we also have a doubler parameter. So all these are easily, we can optimize them and create such parameters using MeshWorks. So moving on. So once these parameters have been created, we can also increase or decrease the number of welds that have been created simultaneously. For example, just say if I'm extending the base of a vehicle, you can see even the weld spot welds will get optimized. So even an entire vehicle model can be parameterized, from moving the position of the B pillar, increasing or decreasing the height of the roof of a vehicle, So all these are possible. Even for a casting component, increasing or decreasing the thickness of a rib or adding multiple ribs as parameter, they're also possible. So these are some of the examples. If you want to add multiple adhesives as your parameter or even convert them into spot welds, so all these are such parameterizations are they can easily be created using the MeshWorks.
Okay. Now, as Aditya has shown us how nicely we can create the morphing scenarios and also how nicely we can create the design enablers, there are some advanced options like auto-parametrizations of auto-parametrization, where you have the model, and now let's say in front of us we have a CRADLE model, and now what we have to do is we have to do some morphing at the members. We have to change the size and shape of the members. So one of the basic idea is where you go directly and do the freeform morphing or control block morphing, or we have some advanced options like now what we're going to see. So what a user has to do is a user just need an intersection lines. That's all is needed. Once the user has an intersection line, a user just has to do some morphing on the intersection curves. Let's say you have to increase the height of the member, you just do a morphing and then increase the height. Let's say if you have to increase the width of the member, that is also fine. You increase simply the width of the lines, and then you will finally you will get your output. Now, similarly, let's take the second intersection. So you can create your own intersections as per your convenience, and you can do the morphing. So this morphing is pretty easy, where only requirement is to do the morphing onto the 1D lines or the CAD curves. Now, let's say if we have an intersection, so the intersections are pretty tough, as you all know, and even the tough joints like this are nicely been taken care only by morphing the 1D lines or the CAD curves. So let's say this is my source and this is my target. Now, what we're going to do is we will see one by one how now this is the flare increase in this particular region. Now we have a tool that is called as a mapping. So mapping will automatically identify the source and the target, and as soon as I say link, it will automatically go ahead and do the morphing. But before that, what if you have to do or create some features? So you can create some features with respect to the 1D line as well. Now, by just clicking on mapping, automatically the inner members have taken the shape of the 1D line, and all the holes, fillets and everything is nicely been maintained, but it is just morphed. Let's take the joint area. Simply go ahead and click on link. Automatically the edges of the link, edges of the member will nicely go ahead and accommodate as per the source lines and the target lines. So this is an advanced auto-parametrization tool which you can take use of in MeshWorks whenever you have to do any topology or regular optimization. So let's go to the next one. So next one is an auto-parametrization again, but now you can use it on a powertrain model as well or a body structure model as well. So let's see how it works in MeshWorks. Now, what if you have to increase the height of the rib? Okay, let's say you have to increase the height. So the user's first requirement is nothing but to select the elements of the rib. That's all has been selected in the first stage. Then the second stage is define the range, that is min and max. Once the elements and the range has been defined, you simply click on review and a parameter is being created automatically within one click. Now we will go ahead and review the parameter. So you move the slider bar and you can nicely see that the rib is nicely moving or increasing up and down. So let's say you have a stress location in this location and this location. What you can do is you can nicely go ahead and do the morphing very quickly and then go for your second round of run. Now, what if you have to increase the thickness of a rib? That's also not a problem. So if you see that this is the GUI, where if you have to increase the rib thickness, you have to select the elements, you have to define the deformable layers and the range. That's all is needed. I'm selecting the elements, that is nothing but the face of the ribs of both the sides, defining the range, giving a parametric name, and simply going and click on execute. An automatic parameter has been created in MeshWorks. If I go ahead and click on review and just increase or decrease the range, then you can see how nicely we can do the morphing on the wall thickness or rib thickness as well. We also have an option where you have a tube. Let's say you have a tube and you have to increase or decrease the diameter. Simply go ahead and go here, select the elements of the tube and just click on execute. We also have an option if you have fillet radius change. What if you have to change the fillet radius? You just have to select the fillet area and give how much you want to change and execute. Now, this was all about the morphing and design enablers. Let's go ahead and move to the next step, that imposing one parameter onto the another parameter. So for that, let's see how it works in MeshWorks. So in front of us, we have a CFD model, and this is an engine block model where we have, this is a parametric file as well, where we have created multiple parameters such as control block morphing, freeform morphing and all. And let's see how we can impose it onto the another model, but I will also like to show you the durability model as well. So if a user has created some parameters onto one model, he can very nicely go ahead and impose the same parameters, same size and shapes, same range onto the another model. And this is the example. Now we can see how nicely we are changing. The locations are pretty much the same, just the mesh elements are changing. We can also see that the water jacket is nicely moving in this particular location and the area nearby. Similarly, now we can see the same parameter has been imposed onto a durability model, and we can see the same changes right here. So this is how we can synchronize and multidisciplinary parameters onto the models. Now let's go ahead and see how MeshWorks comes into play when we have to do any optimization study. So I would like to explain you first this particular flow chart. Now let's say we have some runnable models, that is durability model, NVH model, stiffness models, or CFD models. Once we have the runnable model, you can import it into MeshWorks. Now when you import that models into MeshWorks, you create a parametric file, which means that you create all the different shapes, size, gauge, weld, all the parameters. You can impose it or you can create it in MeshWorks. Now once the parameters are being created, what you can do is, next is define the design variables and the limit. Go to an optimizer. You can use MeshWorks as an optimizer as well, or you can use a third-party software like an iSight or Mode Frontier, where the input is just to define the range. You get the range from the MeshWorks parameter. You impose that MeshWorks parameters range file into the optimizer. Optimizer will nicely create DOE. This DOE Excel sheet has been then imported into MeshWorks again, so that very nicely all the n number of files are been exported out. Now this n number of exported out files are nothing but runnable files, which you can directly link to the solver, and you can create an input-output matrix. Now once you get an input-output matrix, what you can do is you can again give it to the optimizer or the processor, which sees the response surfaces with respect to the objective and constraint, and that's how you get an optimized design. We'll see this step-by-step process how exactly you can do in MeshWorks. Now let's say we have an assembly of an axle model where there are multiple load cases, as well as there are different analysis and different targets as well. Now what if we have to do an optimization study for an axle model? So the first thing what we need to do is we have to create the parameters. As I mentioned, you bring in the runnable model in MeshWorks and you create some parameters. For the diff case, let's say you have a rib pocket depth, inner pocket depth, neck radius, flange, rib thickness, etc. You can see the following changes in here, right here, some are here, and all the changes you can see. Now the next subcomponent is nothing but the brackets or the tubes. So we have nicely created some parameters onto the bracket as well. Now we can see the bracket thickness is changing here as well, and some other components as well. Now what you do is, this is our basic flow chart. Define the model type, define the number of DOE, generate the designs, solve and extract the results, and review the output. Now you have a parametric file, you have a range. Now give the range to the optimizer. Now we'll see how we can give that. For that, you just define a directory first, define a morpher batch exe location so that automatically in the background everything will run. Define a template. This is the min and max range. These are the number of designs which you want to create from the min-max file. And then this is the final output folder. Once you click on generate DOE, automatically an Excel sheet has been exported out. With respect to the algorithm which you have selected, it will nicely go ahead and create 400 different designs with different values with respect to the range which we have. Now, the Excel sheet which you have, we can take use of it in the next step. So for that, what we need is we need a parametric file, whatever you created in MeshWorks. Then we need a DOE file and the output directory. Now click on generate design, and automatically 400 designs have been created in MeshWorks. What if you have to select the design one and see exactly what are all the changes? Design 1 rib height is 8 mm. Design 2, let's go ahead and see. Rib height change is 5 mm. Design 3, let's see the rib height is 11 mm. Likewise, for all the 400 designs, there are different values for the rib. Now what you can do is you define the solver path, result extracted script, and session file. Once all these three inputs are given, automatically in the background, all the 400 files are been run, and automatically an IO table is generated. This IO table defines exactly which is the best output model, and you can also go ahead and create an auto report generation. Now, what is this auto report generation? Let's say you have to see the design 1 report. Just go ahead and click on design 1 report, and automatically you will see all these inputs in your model. You can see component wise all the stress locations and displacement, whatever input you have given. You can also see the assembly level as well. So this is how nicely and quickly you can do an optimization study in entire from 9 years from basic mesh to the final runnable models in MeshWorks, and you can get an optimized model. Now, what if you get an optimized model? What is the next step? So you have to convey the optimized model to the CAD engineer. So we have the solution for that as well. So what I would like to do here is I would like to show the difference between the two models which you can see in the front. Now, in front of us we have a deformed FE file. As you can see, in the previous model as well, we have seen that how nicely we can change the rib height and all. So this is a deformed FE file. I would like to show the baseline FE file as well, or the original FE file. Now the red one is nothing but the original FE file. I would like to show you the difference between the two, the deformed and the baseline. Now here is an CAD also. So we have a baseline. So basically we have a baseline CAD data, we have a baseline FE data, and we have an optimized mesh data as well. Once you have these three inputs, then we have a nice option that is called as an impose deformation, where a user has to select the baseline design, import the baseline FE file and the deformed FE file. As soon as he clicks on impose, automatically a deformed optimized CAD has been generated. As we can see here, a nice deformed optimized CAD is also been generated. So now this you can take use in your internal purpose, or you can take this CAD to the CAD engineer and he can use it for the further requirements. Yeah. So this is all from my side. Raj?
Okay. So looking into all the different options which are pretty much facilitating the entire process of optimizing and achieving a lightweight design, we would like to talk about a case where we did a full vehicle optimization, and here is the mass walk-up. So you can very clearly see there's 100 kg plus mass saving on the body in white design. In fact, we considered the crash, NVH, stiffness, all the load cases. And there's a classic example where we have the load path changes, we have the enablers, we have the G optimization techniques. They all have been considered in this optimization study. So we can see the time frame too, like in a normal scenario, this process of getting all the manufacturable parts with even the manufacturable studies would take close to, 2 years. But with the application of MeshWorks and the CONCEPTWORKS kind of a process, we were able to get it done in a time frame of 6 to 8 months. So we just thought this would be a good example to showcase to the audience. Now let's move back to the next slide where we will see like what are all the benefits. Why do customers prefer MeshWorks? MeshWorks has a 70% faster process for converting the topology automation results to a concept design with zero CAD, and it has robust automation tools with built-in built-in DOE and MDO tools. Our AUTO-PARAMETRIZATION tools for full vehicle makes the entire vehicle morphing process 70% faster than the conventional morphing approach that is currently existing in the market. And you can easily build concept designs without any CAD. And we have a library of design enablers which can quickly enable the performance of your design. We can expect 2x to 10x kind of a time reduction when we use CONCEPTWORKS and MeshWorks in their optimization process to achieve lightweighting. On top of this, we can convert any of the FE models quickly into intelligent parametric models with the help of MeshWorks. So these are all some of the key areas which enables the customers to get more oriented towards MeshWorks for their lightweighting studies.